Okay, here we go. Okay, welcome all. Let's see here. I am gonna do that to get the audio fixed. That looks better. Okay. Sharing screen. Okay. So yeah, real quick, here's a picture of the monkey saddle that I was telling you all about last time. So amusing image aside, you can see that this is definitely different from a regular saddle point, right? This is not a Pringle. So anyway, this kind of thing, and then you can see also there's variations of it. I mean, this is what is that, like a 7-legged saddle, right? I mean, there's all sorts of weird things that can happen in multiple dimensions. Okay, all right. So yeah, so here's what we were talking about last time. If you want to find a critical point in more than one dimension, look for points where f fails to be differentiable. Look for points where the gradient's equal to 0. Everything else you can rule out. Couldn't possibly be a maximum, right? Because of this reasoning, right? But if you, if either one of these things happens here, then who knows? No idea what's going on. Okay, so we saw an example last time, and the idea is this function here, it's differentiable everywhere. So there's no critical points there. Setting the gradient equal to 0, you get 2 candidates. Right? Okay. And then we ended with an example that is just a little trickier, and you have to be very careful about this sort of thing. For whatever it's worth, my experience has been that I don't know, in high school even, we kind of got away with murder with algebra. You just take the square root of both sides of the equation. Don't worry about the whole plus minus thing off. Not our problem. That kind of a deal. And well, you're going to miss stuff with that, right? It's really not mathematically valid to be too fast and loose with the algebra. So when you have something like this, you've got to heads up, be aware, and consider, actually account for in your work that there really are 2 versions of this. There's x equals y and there's x equals negative y. And neither one is more likely than the other, particularly, right? Unless there's a context or something. So anyway, so do be careful with that. And if you find yourself in a case where your algebra leads you to, well, there's 2 possible cases, cool. Actually work out the algebra for each case, right? And all of what you find are critical points. Okay. All righty. So let's talk about the second derivative test. By the way, this goes kind of back now to section 4.1. The book spends a lot of time on Taylor series, a lot of which, by the way, is review, and then some of which near the end is further than we need to go. Okay, so here's a quick reminder of single variable second order Taylor polynomials. So I know you all have seen this before in a Calc 2 class. And so let's think about how we can modify this in the case where we're looking at a critical point. Right? So we're looking at a critical point. So that means the derivative is equal to 0. And if the derivative is equal to 0, well, that means that this term right here disappears, right? That term, it's 0. It goes away because, well, it's 0. And so therefore, all we're really left with is just that, right? Just this business right here. In other words, we've got that the best quadratic approximation, in a sufficiently nearby region, a sufficiently accurate approximation of our function is that it's a constant plus a parabola that is centered at the point we're looking at. Right. So this is a really easy way then to understand, locally what's happening to that function. Let's suppose, for example, that we know that f double prime of a is positive. Well, if it's positive, well, then that's positive. That's positive. A square is certainly never negative, right? And so what you've got there is an upward oriented parabola. And that tells me that this critical point that I was looking at, being at the bottom, at the vertex of this upward oriented parabola, that's a minimum. Right? So this is a pretty easy way to say, a pretty easy way to see that a positive second derivative gives you a minimum. Right? That's part of our second derivative test. And then likewise, you can do it the other way. If this is negative, right, second derivative is negative, well, then it's a downward oriented parabola, and therefore your critical point's a maximum. Okay, so ancient history. Here's the multivariable version of it. I emphasize we're only in this course going to worry about what happens when we have two variables, just two variables. Things do get weirder. Some parts of this get weirder when you have more than two variables. So only two for us. That said, here's what your second order Taylor polynomial looks like. Quick side note, this is actually true for any number of variables, but the part where we have to restrict it to two comes very soon. But there is a sort of a zero order term of just, well, the value of the function at your point that you're working on. Then there's the what you might call first order term, which, you know, it looks a lot like the Taylor first order, to the single variable first order term. There's the kind of the derivative. Okay, now it's a gradient. And then you multiply by x minus a. Okay, but now that's a vector. And so now this ought to be a dot product. It's all kind of plausible, right? And then there's a second order term. And this too is kind of reminiscent of what we had up here. If you kind of look at this and you compare with that, you see that there is there's the 1/2. And then there's two factors of x minus a. Now, they're separated down here, but nevertheless, there they are, two factors of x minus a. And then here, the second derivative, down here, it's a matrix consisting of all of the second derivatives, organized in a certain way, right? In the sort of the most organized way. So it's not entirely unfamiliar, right? I mean, this is kind of, you could say, I guess that kind of tracks, sort of, right? I mean, maybe I wouldn't have guessed this, but it's not outrageous. For your consideration, I think it's a good exercise to confirm for yourselves. Like you may recall way back in chapter 2, and I argued that the linear approximation, we can feel good about our linear approximation of a function by just confirming it has all the correct values and it has all the correct first derivatives, namely all the correct partial derivatives that it's supposed to in its attempt to track, the function that it's approximating. Same for this one, except now not just values and partial derivatives, but also second partials, right? So good little exercise. You confirm for yourselves that this has all the correct values, partial derivatives, and second partial derivatives as the original function f that it's approximating at the point A. All right. So again, doesn't really prove anything, but that's very satisfying that this is what we really ought to call the second order Taylor polynomial. Okay. So how do we study this? Well, in the same way that I previously needed to understand this term to help me classify a critical point. When is this positive? When is this negative? Now I need to study and understand this term. And this is weirder. I can't just break this down as, well, some parts are clearly positive, some parts are clearly negative. There is a matrix multiplication happening here, and then there's a dot product happening after that. And it turns out this is a non-trivially complex object to study. It's called the quadratic form. So you may have conceivably seen this. I'm actually kind of curious. Have you all seen this in Math 218, quadratic forms? Okay, cool, good deal. So this is a quadratic form. And so what we're interested in is this expression positive definite or negative definite? So all that business. Yeah, I know, I see that. All right, so this is why we're going to restrict it to two variables. Being as it is two variables, this matrix here then is only 2 by 2, and understanding whether a matrix is, whether a quadratic form defined by a 2 by 2 matrix is positive, definite, or otherwise, actually breaks down pretty easily. And this is a short list of cases that you have to consider. I'm going to start in the middle here with what I'm going to call the easy part. And that is, if the determinant is negative, game over. You've got a saddle point. It could not possibly be positive definite nor negative definite if the determinant is negative. And if you want to think back to linear algebra class long ago, roughly speaking, what's going on here is you can find a change of basis by which subject to that change of basis, your matrix is diagonal with a positive on one term and a negative on the other term, and that would just make this expression something squared minus something else squared, right? And that's clearly neither positive definite nor negative definite. Excuse me, I'm sorry, I forgot to turn this off. Yeah, but you don't have to worry about that linear algebra side of things. Determinant negative, saddle point. Okay. If the determinant is 0, well, failure. Roughly speaking, if the determinant is 0, what that's telling me is that the quadratic term does not dominate as much as it needs to in order to in good conscience ignore the third order term and fourth order term and higher order terms like that. So determinant equals 0 means this is no help and we really don't know what's going on. Still continue not to know what's going on at these points. So that's the easy part. The familiar version of this is when the determinant is positive. And roughly speaking, if the determinant's positive, then you can kind of revert to, this is what you might have kind of naively guessed if you hadn't ever done any multivariable calculus before or something. You would think, well, let's take one of the second partials. I don't know, pick one. Let's take the x second partial. And if it's positive, you get a minimum. And if it's negative, you get a maximum. That's kind of the second derivative test from single variable calculus. Well, that works if your determinant is positive. But it is very conditional on that determinant being positive. Okay, so let's see this in action. We previously saw this example. We found the critical points. These are they. We freely admitted we have absolutely no idea what's going on at these points. Are these maxes? Are they mins? Are they saddles? Who knows? So let's apply the second derivative test. Nothing to it. You got to take the Hessian matrix. Here it is. Various second partials. Take the determinant. There it is. And now play the game. We're going to do literally this this test up here. I zoom out so we can fit it all on. Here we go. Yeah, so let's look at this point A1. Plug that in, compute the determinant. That determinant's positive. Tells me we're up here. I can also look at fxx, namely that term in the Hessian matrix. It's positive. Again, at this given point, we're looking at the point 1, 0. And it being positive means I've got a local min. Everybody good? Straight up applying the, working the table that we have up there. Okay, and then analogous, was that? No. Okay, all right. Analogously, but now looking at the other point here, -1, 0, you plug that in and you get a negative Hessian determinant. Negative means saddle point. And no further analysis necessary. Yeah.
Does the whole Taylor polynomial part matter here, or is it just where this comes from?
Yeah, that's where this comes from.
Oh,
yeah.
You don't need to do.
No. I just wanted you to know where these. So basically, this big table of rules up here. The reason that this works is because of the Taylor stuff. Right. Yep. Okay. Okay. So good stuff to know. Okay, so on until now, the kind of the more interesting part of what we're going to do today. So this is gets into section 4.3 now, constrained optimization. It gets back to this business about the boundary. You may recall we started off that optimization saying, well, we've got interiors and we've got boundaries, such as, for example, maybe I'm looking at the unit disk, right? And well, I can find critical points in the interior, but separate question, what if I'm looking for critical points on the boundary? And I hinted that the rules would be different, and they are going to be different. Right? We're going to have different rules on that boundary. So the boundary, you'll notice, is a circle, but more to the point, you'll notice that it's described by an equation, and that's called the constraint equation. I suppose not every boundary is immediately and given as described by an equation, but if you're going to apply the analysis that we're going to do here, we need it to be described by an equation. Yes.
Is this just in 2 dimensions or any dimensions?
This works just as well in 3 dimensions. Yeah, absolutely. I'm just gonna, it's easier to do the pictures in 2 dimensions. Yeah. Okay, so all right, so we've got this thing called a constraint equation. Notice that I've got this constraint equation written as a level set. Now, again, it might not come to you in that form, but it's easy to put it into that form, and we need to put it into that form because we need to view the constraint equation as being the level set of something we can then call the constraint function. And that constraint function is going to be really, really important. So anyway, there's our terminology. Okay. All right, and then yeah, same deal in 3 dimensions. Now in 3 dimensions, instead of having a 2-dimensional interior with a 1-dimensional boundary curve, here we have a 3-dimensional interior with a 2-dimensional boundary surface, right? But it's nevertheless still described by an equation. That's my constraint equation, and it's a level set of a constraint function. Okay, so now where we go with this, I'm getting ahead of myself. Quick observation. There is something confusing about these constrained optimization problems, and that is there are 2 separate functions that we're dealing with. So for example, here we're trying to maximize that function subject to a certain constraint. Okay, well, there are therefore 2 functions involved. There's what we call the objective function. That's the function we're trying to find the biggest value of, or the smallest, whatever. Then there's this separate thing, which is the constraint function. Now, notice these totally different functions. And in fact, there's no particular need for them to be related at all. They are playing different roles. One is telling me what I'm trying to make as big as possible. The other is telling me the rules that I must adhere to while I'm trying to make the first function as big as possible. So anyway, make sure to keep these straight in your mind. You don't want to avoid phrases like the function, right? Because there's 2 of them. Very important. Which one are you talking about? Right? Okay. Okay, so here's a couple of quick observations. Time being a factor, I'm going to be quick with the details here. I'm going to hit what I think are conceptually the big points. Because we are looking at a level set of the constraint function, the gradient of that constraint function is always orthogonal to that constraint set. And this is just a warmed over restatement from what is it, chapter 2, I guess it is. Gradients are always perpendicular level sets, right? So here, the constraint gradient is always orthogonal to our constraint set. Yep.
The constraint set is the level set of the constraint.
Yep, that's right. Yep, exactly. Yep.
So in the previous example you just said, where you said like on the sphere, x squared plus y squared plus z squared equals 1.
Yep.
G dx squared plus y squared plus z squared.
Yep, that's right. Yep, that's right. So that's right. So the function whose level set gives you your constraint equation, that function is your constraint function. Yep. Okay, so the constraint gradient's always orthogonal. So here's kind of the meat of the analysis that we're going to do here. Here's my constraint set. Here's my constraint gradient. Again, always perpendicular. In fact, it kind of defines this orthogonal line here generically. And now let's just consider, what if, hypothetically, what if our objective gradient is off axis? What if it's not pointing in the same direction as the gradient? What if it's not perpendicular to your constraint set? And the real easy argument that I'm going to make here is, well, if it's pointing off axis, then it's leaning in a certain direction. I can just go in that direction. And as I go in that direction, the function's increasing. And therefore, this couldn't possibly be a maximum. Check it out. The function's increasing as you go that way. Now, this is a slight variation of the argument we made in the unconstrained case. In the unconstrained case, we said, hey, just go in the direction of the gradient. Well, I can't here. I'm stuck on the constraint set. I'm not allowed to leave that blue constraint set. But if it's leaning off axis like this, then even though I can't actually go in exactly that direction, I can go somewhat in that direction and it's still increasing. So basically, you can eliminate any case like this, any case where gradient of G and gradient of F are pointing in different directions because, well, function's increasing. Couldn't possibly be a maximum. Same, morally, the same argument that we made in the single variable case. Okay, now there's some details here that y'all don't need to worry about. I'm going to jump down to the punchline here of how you work with this. Here's what we just wrote down. Effectively, the gradient of F needs to point in the same direction as the gradient of G. Namely, it needs to be a multiple of the gradient of G. And there's a couple of little exceptional cases, and you got to worry about implications and writing things in a way that's algebraically useful. The punchline is there are three conditions to check. Of course, you got to check for differentiability. If the function's not differentiable, you can't compute directional derivatives at all. And you really don't have any way of knowing what's going on there. This is what this is what we call the Lagrange condition. This is the kind of the picture of what we drew here. This is the, the picture of every case other than what I drew here, right? If these vectors were parallel, then I would not be able to make this argument. And then for reasons, again, a little on the hairy side, and let's not worry about it, but if the gradient of G is equal to 0, this ends up being a big deal. This is called the degeneracy case. And if that happens, if your constraint gradient is the 0 vector, you have to call that a critical point. And the very, very loose version of why is because check out this picture, right? This is possible. Your constraint gradient is the 0 vector, and our actual objective gradient is perpendicular, and so I can't actually conclude, I cannot eliminate this as a possible maximum, but also this one's not a multiple of that one because nothing's a multiple of 0, and so that condition doesn't catch it. There's a very short version of why we have to check that third condition. So anyway, these are the three conditions. This is what we check. And if you have a constrained optimization problem, go 1, 2, 3, go through these three conditions, identify your critical points, and there you go. So let's see an example. Here's a constrained optimization problem. Constrained optimization problem. Again, reminder, you gotta be very careful. There's two separate functions in play. Don't conflate them, right? We have the objective, the thing we're trying to maximize, and we have the constraint function that describes my constraint by way of a level set. Okay, so there's my two functions. Yeah, we know we're going to have to compute both of those gradients. Here's my objective gradient. Here's my constraint gradient. That's just algebra. Just, take the appropriate partials. And now let's start checking conditions. Where is this function differentiable? Well, it's a polynomial. It's differentiable everywhere. Now, I do want to emphasize one thing. Notice how easy it is very often, right? Usually, dare I say, usually really easy to check that condition. Some students take the wrong lesson from this. and think, well, it was easy to do, therefore it couldn't possibly be useful, therefore I'm not going to bother. That's exactly backwards. That's exactly backwards. It's one of the three conditions that has to be checked, and you can do it by you. You can note I didn't even say hardly anything. I just said differentiable, right? One word, right? Write the one word. You've checked a condition, and that's worth points, or at least point. I don't know about anyway exactly how many, unclear. But please don't make the mistake of I'm not going to bother, right? And don't not writing that down. That would be a huge mistake. You definitely want to check the differentiability condition. Okay. Next, I'm going to do the degeneracy condition next because it's so easy also. But again, don't forget, don't leave those points on the table. Right? Dare I say free points. Right now, in this case, it happened to be really, really obvious that this was never zero because, well, it's a constant that isn't zero. Therefore, it's never zero. Right? I mean, that's world's easiest argument. But sometimes it won't necessarily be that easy. But the point is, you have to check it. Okay. And then lastly, here's our Lagrange condition. Right. Notice that our Lagrange condition boils down to I need for this that has these three components to be a multiple of this, which has these three components. And then, of course, that Lagrange condition can be rewritten as this trio of three equations. Yes?
Could we also just look at f and g and say, well, if 2x equals 6, then like our multiplier has to be 3?
Yeah, I mean, that's what we're eventually going to do. We're eventually going to start analyzing those equations. But the point is, write the equations down first, and then the analysis is coming. Yep. I mean, you're going in the right direction, but don't skip steps and get it all written down first. Yeah. Okay. Okay, so we've got our Lagrange condition written down, but before we go into that, I want to remind students of another thing. It's also easy to forget, and that is, why are we looking at the Lagrange condition? And it's because we're trying to find points on our constraint set that might be critical points. Let me say that again. Points on our constraint set. So don't forget, you're only interested in Lagrange condition on your constraint set. You're not even allowed to look off of your constraint set. So don't think of this as, well, I've got 3 equations. No. You've got 4 equations, which is good because you also have 4 unknowns, x, y, z, and lambda now, right? This scalar, known as the multiplier, thus the term Lagrange multipliers for this method. So 4 equations and 4 unknowns. And here's where, yeah, I mean, this is now you got to solve. And solving a large system of equations with, large number of unknowns, well, it's hard. And you might get lucky and everything might be linear. In this case, it happens to be linear, right? But it often won't be. Usually even won't be actually linear. And so it's tricky business. So I'm going to show you how this one works out. And this is a surprisingly common strategy, and that is to eliminate the lambda. So namely, solve for that lambda in all 3 of these equations, and lambda in the first equation gives you that, and the second equation gives you that, and the third equation gives you that. Well, all 3 of these things that I just solved for, I was solving for the same lambda in all 3 of them. And so therefore, these things all equaling lambda, they are also all equal to each other, right? And having done that, notice that that allows me to relate x and y and z pretty well, right? So a huge amount of benefit there. So that's a big trick. I don't want to say it always works, but this is a great, this is the one that works most often, perhaps, right? Now, of course, this alone does not allow me to solve for x, y, and z, but I can take those and put them into this equation, right? Our constraint equation. Our constraint equation becomes this which tells me what X is, which I can then put into there. And then these equations then tell me Y and Z. Now that's how this one here happens to work out. It won't always play out exactly this way, and the algebra is different in every example, right? I encourage you to look at my old exams, but by which I mean my old Math 212 exams. There's a bunch of Lagrange multipliers examples on my old exams. Different questions, different answers, all with solutions, of course, right? So study those solutions, see how the algebra it's different in every example. And I am going to show you one more example in just a moment. So first, I want to observe the next pair of pages, 2 constraints you're not responsible for. We're not doing that in this course. You can ignore these 2 pages. If you're curious, give them a look. The real world is full of 2 constraint scenarios, but we're not going to cover it in this course. So we're going to move on now to global extrema, and I'll remind you of this theorem that says under certain conditions, a maximum exists. Absolute maximum exists. The function has to be continuous. Good news, most of the functions we deal with are. The domain has to be closed and bounded. That's easily checked. Does it contain its boundary, and can you put it in a box? And with that being the case, you can just proceed to checking the interior and the boundary separately. So this will be my last example, and I have to move super fast here, but objective function. And looking at the boundary, as I'm going to sort of move to, you'll see here our constraint function. So objective and constraint. You think about the usual stuff, but here's what the Lagrange multipliers system turns into right here. And it's tempting to reason as follows. Lambda has to equal to 1, right? That says lambda equals 1. I propose for your consideration. But this says lambda is equal to 1/4. Done, there aren't any solutions. Very, very tempting, but I was playing too fast and loose with the algebra. A lot of high schools are very sloppy about allowing students this move of, oh, just cancel the such and such. And so I just very easily swept under the rug that, oh yeah, I'm canceling the x's. I was assuming that x was non-zero. It doesn't have to be. X could totally be 0. Right? So that's the thing. I mean, if if y and z are both 0, for example, if y and z were both 0, then sure, lambda could be whatever. There is no contradiction here. Right? So be very, very careful with your fast and loose algebra. So I think the best way to analyze this system is to break it down into 3 cases. We know at least one of the coordinates has to be non-zero. I mean, after all, we're on the boundary of a solid ellipsoid. We're not at the origin. At least one of these coordinates has to be non-zero. And so consider those 3 cases separately. And if x is non-zero, then yeah, you can cancel the x's, in which case lambda is 1. And then if lambda is 1, you can plug that into these equations, and they instantly tell you that y and z have to be 0. And then you can plug into the constraint equation. Oh gosh, the steps, so many steps. You can plug this into the constraint equation and conclude that x could be plus or minus 6. So again, that's a lot, right? But the sloppy fast and loose algebra was that there were no solutions to the Lagrange system. The reality is there's 6 of them, right? So you can't be fast and loose with the cancellations and the square roots without the plus or minus, and got to be really careful with all that stuff. Everybody okay? Yep.
Wait, so why do we find those? Don't we just say y is near 0? So don't we just plug that into the
You're talking about in this case? It just happens to be an algebraically convenient foot in the door sometimes. And in this case, it is literally in the case where X is not 0, figuring out what lambda is, solving for lambda there happens to be useful because that allows me to then plug into here and draw conclusions about Y and Z. Yeah.
Just
I-
F equals 0. That's-
Yeah. Yeah, absolutely. That's a very strong conclusion, right? So solve for them, in other words. So lambda is a weird thing that we don't actually, in the final result, we don't actually care what lambda is, but it is part of the equation, and it happens to be that finding it or solving for it first tends to very often be the right foot in the door algebraically. Yeah, it's kind of counterintuitive, I'll give you. Yep.
Can lambda be 0?
Sure, could be. Yeah, absolutely. If lambda is 0, let's come back up here to this equation. If lambda is 0, all that's saying is that the objective gradient is 0. And yeah, perfectly fine. And that would indeed be a critical point. Yep, no problem.
So why didn't we do that here?
Why didn't we?
Like you didn't write that as an option.
No, but I did. See, it is one of these options. That's the possible. I'm accounting for that when I say this because because lambda is allowed to be 0.
Well, you wrote the cases where lambda is 1 and 1/4 and stuff, but you didn't write when lambda equals 0.
Because I don't have to. I mean, so the cases that I'm considering just need to be exhaustive, right? So any case that I can dream of that could possibly work has to be in one of these cases, right? Whether lambda is 0 or not 0 or whatever, right? I know that at least one of my X, Y, or Z, at least one of them has to be non-zero because I know the origin doesn't work. So you don't have to enumerate every, it's possible that the sky is blue. It's possible that, my dog's name is Jack. It's possible, right? As long as what you've written down accounts for every possibility in some form or another, whether they're represented in the algebra that you see doesn't matter at all, right? So the lambda equals 0 is part of it may be part of several of these, right? But you don't have to say so explicitly. Does that make sense?
Well, because right here it looks like lambda equals 1 for all of those cases. So
Well,
I can
yeah.
see where like lambda equals 0 fits in that.
What I've done here is shown that in this case, it is in fact not possible for lambda equal to 0. So that possibility got eliminated inadvertently throughout
Sorry,
this.
I thought that you told him that was
No. I was assuming your question was general, like in general, can lambda be 0? Yeah. In general, it could be. There's nothing saying that it can't. It turns out in this example, it can't, but in general, it could be.
Okay.
Yeah.
I understand.
Okay. See y'all on Wednesday. Good luck preparing for the exam, and yeah, have a good one.
Is this the, we have to look at this and it's the wrong example?
Well, it's that is all arbitrated by the schedule, which I do have to wait until the end of class, but I am anticipating putting all of chapter 4 is going to be included on homework 14, and it's all fair game. That's right, the blue color indicating it's all fair game for exam 3. But wait until I put it down here because until I finish class for the other 2 sections.
So 4, 1, 2, and 3, all the homework is due on Wednesday. I only covered 4, 2.
Yeah. I'm sorry,
What do you do?
we just did 4.3.
Oh, that was 4.
Yeah.
What is 4, 1?
4.1 is that stuff about Taylor series, and there's very little in there that's relevant to us, and the homework exercises accordingly are very few. Yeah. Okay, all right, see y'all later. See you. Okay, let's see here, stopping. Okay, and